All right, I think we are ready. Last time we did some SolidWorks and topology optimization, and we were trying to make a topology optimized stand for our X30 that we've been working on. It's over here. I can move it. You know, this guy. We were trying to make something that kind of fit under here and held it up. We did make something, and it did do the generative design. It wasn't particularly interesting looking, probably just because it doesn't take a whole lot of force to hold this up. But I kind of, let's see, I said it was like 3 pounds maybe, and this is only like 1 pound, and I probably didn't give it enough material to work away from, and we could have run it a couple of different ways to see if we could get a different end result, something that looked more like the generative design you expect. Probably could have just asked for a higher weight reduction. I think I did maybe 40%. We could have done maybe 70% or something and come up with something that was more skeletal looking, that just looked neater. Anyway, I didn't print that one out. But we did do that. We did a few other things. Today what we're going to do is we're going to do the same idea, but we're going to use generative design. So this is in Fusion, and it's very similar process, except that in SolidWorks, when we did topology optimization, we built something that was the stand. It was kind of just bulky, and but it would be the stand, and then we put simulated loads on it, some constraints, and SolidWorks did finite element analysis, FEA, to eat away at the unnecessary pieces of material. So we're going to do basically the same process, except that what Fusion's generative design will do is it will go in and we give it some constraints and some loads, and it will generate material between those, whatever we give it, and generate some topology that we can look at. The other thing that's different is SolidWorks ran locally on my machine and did all the calculations here, and it probably took, I don't know, we didn't keep track of it, but 15 minutes or so to generate the design. That was SolidWorks. Fusion is going to take our constraints, send them to I think a Amazon Web Services client somewhere, and run them in the cloud, which does a couple of things. One, it might mean that it takes longer because now we've got a queue, we've got to send these things, we've got to receive them back. That part doesn't take terribly long, but we're not running it locally. But it does also mean that we could send a whole bunch of things, like different options, and we could get all of them running at the same time. Both of these options, well, neither of these options are free. SolidWorks, you have to have the simulation premium in order to run the topology optimization. Fusion, you have to pay with, I think they're tokens, or I don't remember the exact word. We'll have to look at it and see. Now, in our case, the education licenses will let us do both of those for free. Actually, I have not tried the Fusion one recently. The last time I did it, it was for free for the education license. So hopefully it still is. Otherwise, we won't be able to do that part. All right, and then while I don't know how long it's going to take. So to do the actual processing. So we may not get to the process results today. If we don't, then they will come back later, and we'll do that on Friday. But in the meantime, once we've sent away our files, we've got some stuff over here. We wanted to do a nozzle change to a larger diameter nozzle and see if we could get some interesting results with that. And then I also have this, this bed that we haven't printed on yet. I haven't even printed a test print on it. So this is one of the, you can kind of see that it's not lit up. It's just diffracting light from the pattern that's on it. So that pattern should get impressed into our part, and something like this will show up on the bottom of whatever we print. You do have to be careful with these. For one, they don't stick quite as well as your PEI sheets, and if you scratch one, like maybe you get the nozzle too close to the bed and it grinds into it, then that pattern's gone. Or if you get your part stuck on it too well, then and you're having to scrape it off of there, you're probably gonna. I did have one like that. I don't see where it's at now. I'll dig it out later and show you what happens to them. It doesn't ruin the whole bed, but that one area wherever it gets scratched isn't going to do the pattern anymore. Let's go to Fusion. So we're going to try and do basically the same thing that we did with the SolidWorks version, where we're trying to make something like the stand for this X30 plane. So we're going to create, let's create a sketch. Let's see, I wish I knew, oh, there's the labels over here. I was wondering where, I assume Y is up, but I don't know. So let's do that. So we're going to sketch on this plane. And what we need to do is we need to sketch in the stuff that we need to have. So we can't just tell it, generate a stand. And now there are AI models. We could try that at some point too. Not in Fusion, or at least not yet in Fusion. But we could go to one of the meshy.ai or one of those AI mesh generators, and we could try that and see how it works too. I suspect we would need to do a lot of editing, but we'll see. So what I do need to do here is I do need to give it some geometry that it has to have. Basically, it has to interface with the plane, and it has to interface with the actual stand, like the base of the stand. So those areas I need to put in. And when we did that in SolidWorks, I don't remember the exact numbers, but we did something like a little rectangle at the top and a flat rectangle at the bottom. So let's create those. Rectangle, we'll just do a 2-point rectangle. And let's line it up with the center point here so we can find it later. I notice I'm in millimeters, so let's change this. I made this 2 inches by I don't remember, I think maybe a 1/2 inch wide. No, but it ended up 0.75, I think. And from our base, which I don't have, let's go ahead and make our base part 2. And then we'll dimension it so that they actually make sense. Let's put it kind of somewhere down here. And let's say, I think I said that in the preserved region part for SolidWorks, this thing, I think I made it maybe stick with 1/2 inch. I don't think I ever specified this dimension, but I'm looking at the plane over here. Let's say this is, I don't know, 4 inches. Try that. And I did say that I believe between maybe this point and the bottom was 6 inches. I don't remember, there was a 6-inch distance somewhere in there. Oh, it moved it the other way. Not what I wanted. Oh no, it just moved it down. Okay. That's okay. I wanted it on that center point, but I guess this is fine. Alright, so now we've got kind of the base and this peg where it's going to go up into. It's got to drive something in between here. This looks like it's too narrow. Let's make this bigger. Let's make this 6 inches also. That's actually looking pretty cool. Well, it doesn't look like anything right now. What I'm envisioning looks like it will work. So let's do that. Now we need to give these some thickness. Now I am going to also on this one take advantage of symmetry when we get to the fusion part. So I'm going to use these as mid-plane extrusions. So I'm going to, how do I do this? Two-sided, symmetric. There we go. And let's make this 1/2 inch maybe. Let's see what that looks like. Yeah, that's doable. We'll round that off. Oh, I didn't extrude the other part too. So let's bring that back. This one needs to be wider than that. So let's extrude it. Also symmetric. And Actually, let's just pull it out until it looks reasonable. Oh, you know what I did on the SolidWorks was, this wasn't the base, this was just the little tab that would stick into the base. So let's also make it the 0.5 inches. That could be why it's not making a particularly interesting shape. Let's make it wider so that it will taper as it goes up. So let's see what 1 inch looks like. Maybe 1.5 inches. Oh, I think I erased the I. There we go. Okay, now let's, I filleted these corners on the SolidWorks one, so let's do that. So that corner and that one, oh, I think I have to do them one at a time. No. And let's get the other one. And let's make that 0.2 inches maybe. Yeah, we'll do, that's fine. And then let's, what should we do with this part? I'm kind of making it differently than we did the SolidWorks one, so the results will be different. Maybe I should make this, I don't know. Let's just fillet the corners again, and see where that goes. Let's make it 1/2 inch fillet radius. Yeah, that's fine. All right. So there's, kind of looks ordinary. Let's save it, because now Fusion doesn't have as bad of a time at crashing. And most of the stuff it actually does save, it saves, well actually all the stuff it saves to the cloud, unless you export something and then it's a different thing. So let's say that that's our starter geometry. Now, the thing is with the generative design, if I just told it I've got a load up here and this part's stationary, it's probably just going to send material straight up to that, because that would be the obvious thing. But I wanted it to curve. So in order to force it to like make this path around here, I have to give it an obstacle in the middle that it can't go through. So I'm also going to create a sketch, which I could have created the first time, but I don't know, didn't. I'm going to force it to go around this circle. Well, it'll be a cylinder when we're done, but let's extrude that guy in symmetric, and we'll just, I'm not caring about the distance, I'm just going to pull it out there. So now it cannot put any of its generated geometry in this region, or it can't once I tell it that that's an obstacle, and that'll force it to make that curved shape around there. Now it might do some weird stuff here that might have this circle too big, but you know, we'll see what happens. All right. Now we've been in the design workspace, so if we click on that and we have access to it, there is a generative design workspace, and there's a lot of others too. But let's go to the generative design. And oh, this is new. I haven't done one with this. So apparently it can generate fluid paths also, but we're just going to do a structure. Let's see what the fluid path example looks like. Huh. Might have to try that sometime. All right. So here's our parts that we made, and across the top and down the bottom, or down this column here, are kind of the steps. So we can turn the learning panel that kind of walks you through that. We can turn that on or off. We could create a generative study, new one, but here's where I want to go right now. And there are edit model features here, so we could basically edit our model. But let's look at preserve geometry. So we want to preserve this body and that body, because those are the ones that we say are the base and the little tang for integrating with the plane body. So we want to preserve those. Okay, and then obstacle, we want it to avoid this thing, and so that's kind of all there is to that part. We could give it a starting shape. So if we give it a starting shape, then it's basically doing the topology optimization that we did with SolidWorks. So I'm not going to do that. I'm just going to give it the starting preserved geometry. Symmetry plane, we do want symmetry. I don't have the planes turned on. I have to turn them on. The way I built it, this plane here is in this very center, so that'll be our symmetry plane. What else do we have in here? Oh, so we could have given an offset. In our case, the obstacle, I just made it the exact size I want it. Well, the exact size I wanted it. But in this case, they're kind of showing the example of, hey, you've modeled up this wheel. You need some space around it for clearance. So you could use the wheel geometry and then just say, hey, I want an additional 5 millimeters of offset space around it. So you could do it that way. We don't need to do that. Let's see about our constraints. So fixed geometry. We want this guy to be fixed. So we'll end. I'm trying to think if I should fix any of this or not. We're going to preserve it, so I think it can't move it anyway when it's preserved. So we're going to leave that free to move in the deflection sense, but it's preserved through the geometry. Let's put some forces on it. I don't know what this little arrow is telling me. I'm not sure what that one's telling me. But let's do some loads. Let's just put a force. And last on the SolidWorks, I put 3 pounds right here. So let's do the same thing with this one. Except it doesn't like pounds for some reason. Oh, I have to change the units. Okay. The units are over there. Oh, and it wants LB force. All right, I typed LBF. All right, there's our 3 pounds on that surface. What else do we have? Different kinds of loads that we don't need for this case. Now some objectives. All right, so over here, or I'll move it. Minimize mass, maximize stiffness. We want to minimize mass. Safety factor. We weren't able to put a safety factor in SolidWorks because the material I assigned didn't have a yield strength associated with it. So we actually turned off the safety factor part. Here, we haven't even assigned a material yet. That's actually going to be part of the simulation. Is we can choose all sorts of materials. And what if we printed this in steel, or what if we machined it out of aluminum, or what if we well, again, FDM printing isn't the kind of 3D printing they're talking about. So you have to keep in mind that it is assuming kind of a resin SLA type print where the material, the printed part, is mostly uniform strength versus a FDM print that has weakness along the layer lines. But let's leave that. We could actually add in some natural frequencies, displacement buckling. Let's just say that minimize mass is our goal. Manufacturing. So here, this one is, we have several options here. So do we want it to be additively manufactured? So yes, we do. We could select unrestricted, and it just makes a random, it's not considering that, oh, this has to be printable, or oh, this has to be machinable. So we could do unrestricted and just let it go. But we're going to leave additive on, and the orientation, let me see, let me make sure I'm getting this right. Sets the 3D printing build direction parallel to the Z-axis. So are we going to build it up from the bottom, the parallel to the Z? So the Z-axis is basically, or the Z plane, the ZX plane is this bottom plane with the lock on it. So do we want it to build up that way, or do we want to print it some other orientation? And if we include all directions, then it'll just try all the orientations that it could print. Let's say, I don't see a better way unless we printed it in 2 halves and glued it together. So let's say that yes, it's going to be parallel to the Z positive orientation. Overhang angle, so this is where it's going to say that, hey, if you need supports, or well, if you want a certain angle, you're going to need supports for it. What is that angle? So most printers, FDM printers, are totally fine printing without supports as long as any overhangs are 45 degrees or steeper, so closer to 90 degree vertical. Some printers can do better than that. So some printers can print overhangs that are maybe 60. Now I don't know which way they're measuring this angle from, though. They're measuring it from vertical according to this picture. So sometimes the overhangs are measured from horizontal, so you have to be careful which way you're actually measuring from. But according to their picture, we're measuring the 45 from vertical. And that's a safe number for pretty much any FDM printer. Can print 45 degree overhangs without support and no problem. But your printer may be able to do 60 degrees or more, and that gives you more options on what the final part will look like. Let's leave it at 45 because that's a safe number. Minimum thickness. So also when you're 3D printing, some of these generative designs could generate super thin little tendrils that are supporting the thing, and those may not be big enough to actually resolve in your print. So 3 millimeters is plenty big enough for FDM printing. You can probably go down to 1 millimeter and get away with it, but now you do have some pretty small little pieces it might have to print. Plus, it also means that your print's going to take longer because it's got all these little 1 millimeter points it has to make. So 3 millimeters is good starting point there. We can also say, well, what if we wanted to mill this? So we could add different milling operations, which will mean that it can only generate certain geometries because you can only mill. This is 3-axis milling. I think I have other options. So I could say that it's just 2.5. Basically, it's just top down. 3-axis gives me more of something that looks like the 3D printed thing. And then the 5-axis, it can do all sorts of undercuts, because the tool head moves. Well, usually with 5-axis, it's on a trunnion, so the part swings back and forth, and the tool head just goes up and down, or left and right. But let's, just to have a very different thing, let's do 2.5 axis. Tool direction is orients the tool in the direction parallel to the z-axis. Yes, so that would come in from the side of ours and cut out little pockets. That sounds good. Minimum tool diameter. So this will kind of be dependent on what you have available for your mill, but larger diameters will obviously be able to mill faster, bigger chunks of material, but they can't make very fine radius cuts, because they have a certain diameter. I think let's actually go down to a 5 millimeter so that we can get more detail out of this. Minimum wall thickness 5 millimeters. Same idea with the minimum thickness on the printing is when it gets too thin, it either can't make it or it's not very structural. Then we also have these two. I'm not going to turn everything on. Well, why not? Why don't we do it all of them on? As long as it will do it in the cloud for free. If it won't, then we'll change it up. But 2-axis cutting. So you want to throw it on the water jet and just cut the part out. So that seems good. Casting. Maybe you want now ejection direction is really referring to like injection molding and which way is it going to come out, but it's also mold removal in sand mold or whatever. I think for our shape here, the Z direction for all of these is ideal. That's also why I built it with the Y-axis up in the way that we built our preserved and obstacle geometry. Draft angle, when you're talking about casting, injection molding, casting, that sort of thing, where there's a mold and your part is formed inside there and you got to remove it. If you don't have a draft angle, then it gets hard to remove. So the draft angle is in this little pop-up window here. The sides, the pink silhouette there, cross-section view, is not vertical. The sides are not vertical. They have an angle on them. That's the draft angle measured from vertical. Well, measured from your release direction, I guess. And then same thing, minimum thickness. So that has to do with, can it at some point it's too thin of a cavity to fill with either aluminum, if you're like aluminum sand casting, or even if you're injecting plastic under pressure, there's still a minimum thickness of, you can only get so much material into the mold before it cools if it's really thin. And sometimes it doesn't cure right if it's really thin. So we turned on all of those. Here we've got our materials. So what are the materials we want to try making this from? So let's add in some options here. So for the additive, actually we could probably, additive, let's not do aluminum. Let's do a plastic. So let's get rid of the aluminum. How do I get rid of this? Delete. That was a right click. Now again, these plastics are not FDM plastics. These are all, well actually these are really tough materials. What's the closest I see that we could actually print on a printer here is this nylon, maybe the nylon 11. Now these are not the nylon that we would print, but these are, well, we can print a PA11. Actually, I think a lot of times it's a PA12. I saw one here. There's a nylon 12. But these are resins. So that's close-ish to some of this stuff that we can print on an FDM printer. These others don't look close at all. Let's look in our milling. Let's say in milling, 6061 aluminum, that would be cool. Cutting is the same. Casting is a slightly different aluminum. Let's actually make our mill one. Let's make it out of steel, just to have a different material in there. So, or there's a stainless, titanium. Wow. Let's just do the stainless. All right, just to have a different material. All right, so you can go through and select your available materials to print, cast, cut, whatever. You can manage and create your own materials. We're not going to do that. And then we're in the pre-check phase. Let's make sure that there's nothing. All right, so on our 2-axis doesn't support preserved bodies of different heights. Oh, that just makes sense. So that's okay. I'm not going to change the preserved geometry, but it is right that it might not be able to make this in a 2-axis method. And same thing here. We may have to turn off the 2-axis cutting. So let's go back to our, that was in manufacturing. Let's turn off the 2-axis. Because of the way that I made it thicker at the base and thinner up here. You could do that. You'd have to flip it over and mill the other side and fixture it and all that kind of stuff. So let's do another pre-check. I turned that off. I guess it kept that. I'm pretty sure I turned that off. Yes, I turned off the 2-axis, although casting might count as... Oh, no, I did 2.5 axis on the milling. Let's go back to 3-axis then, I guess. Now our pre-check. Ready to go. All right. Previewer, so we could locally, without sending it to the cloud, get a sample. Why don't we do that? It doesn't take terribly long. Oh, I really didn't want it to put material over here. I wanted it to all go around that way, but I guess if I don't want it to have something over here with just a hole in the middle of it, then I need to probably go in and make some obstacle geometry on this side. So that's why we preview. And that'll force more of it to go around that direction. Because, I mean, that's not what I wanted at all. So let's go back and actually put some geometry over here that will force it to not be able to go on that side. Let's go back to our design. All right. And let's create a sketch here. And let's make sure that it can't go over there. Oh, let's see. project that line. Why are we stuck? Alright, I think it was just taking a while. Oh, I should have projected down to here too, so it doesn't want to go down there. Yeah, I'm too deep there. It might need some room to do something down there, so let's do more like it might need to do something. Actually, why don't we make it tangent with our circle, or close to tangent with our circle. All right, so that'll work, I believe. And then let's extrude that guy symmetric and just pull it out, something like that. Oh, but we want to join. Oh, wait. I think if I join, it will end up joining it to this the way I made it. So let's actually do this. Create a line. Let's go back to our sketch. Are we still in it? No, let's edit our sketch. Let's make it where it doesn't go right up against that guy. There we go. Yes, that's fine. So if I make it part of that one, then I'm afraid it would get confused. And let's join that together. I'm not worried about it being particularly, great looking. Go back over here, and since it's part of the circle, it automatically made it, since they overlap, it made it also preserved. What I was afraid was going to happen is it was going to be touching the circle and the preserved, and it wouldn't know what to do with a preserved region and an obstacle at both touching the same part. So that's why I made that little gap there. All right, so pre-check still good. Yes, let's do our little previewer, see what it comes up with this time. It still wants to put some weirdness over here, but at least it's going around there. I don't know why it's dipping down. It should eliminate those because they're not doing anything. It's just, I think, trying to figure out, where does the geometry, can it exist? Now it should, notice it's iterating a little bit and moving more of it over here. That's at least starting to look more. It should eventually eliminate all of this, and all of that little hump. Good enough. All right, so now we go to generate, or stop preview, and let's do generate. All right, so yes, good. So in the education account, I have an unlimited amount of credits. Cloud credits is what they are. It says it's going to take 11. I don't remember how much a cloud credit costs, but I would need 11 of them. And I think they're like $100 each. But with the education license, at least the one I have, you can do these still for free. At some point, that might not be true. So I click select or whatever, and it is sending my constraints over to the, I think it's the, like I said, Amazon Web Services, but whatever cloud system they're using, it's sending it over there, and at some point we will get it back. Once it's sent enough, here we go. We will start getting thumbnails. I think I can close this window without anything bad happening. So I wanted to see some of the thumbnails to see what we're going to get, but I don't know how long they're going to take to start showing up. If they don't show up soon, then we'll go ahead and start working on our other stuff. Yeah. Hasn't done much of anything yet. All right, well, I'll let it run. Again, I don't know. We should get some of the at least intermediate results before classes. Oh, well, there we go right there. And it's the first ones are not going to look great. They're basically the preview, and they're all identical. No matter which, I've got 4 different ones. It looks like it decided to run. And 2 of them have at least some first iterations, and 2 of them don't have any iterations. And it looks like I've got 1 for unrestricted. That must be the first one. Let's see. No, it was actually that one in the middle, I guess. And then additive one, the 3-axis mill, and the casting one. And so it's come up with, the starters for one of these. You can kind of get a preview of what it's doing. Nothing exciting yet. This one is the printing one because it's using the nylon here. So this is the 3D printed first iteration. So we'll let that go for a while. These will continually update, and hopefully we'll get something more interesting than any of these. Right now they're just the first step iteration. So at this point, it's created the first step, and it's basically creating some geometry now. It looks like some of these are on step 2. This one looks like it might be on step 3 or so. And it's starting to do very similar to what the SolidWorks optimization was doing, with the exception of, except for obstacles, it will create geometry outside of the geometry it created the first time. So it will, move things around more than the SolidWorks will, while it still respects any preserve and obstacle. So we've already got a couple of options here. So we've done 5 iterations, kind of looking like a microscope. So you can see where it's preserving the parts we told it to preserve. It's avoiding the parts we told it to avoid. And then it's trying to connect the dots between there. Not looking super interesting, but it's only done a couple of iterations. Actually, this one looks kind of cool. Well, this view of it, I don't... There's actually essentially no stress on... Oh, this is the steel one. No, this is aluminum. So yeah, with 3 pounds, there's essentially no stress at all. So we'll let it go. It should be able, on those metal ones, it should be able to, even the nylon, should be able to eat away most of the material. But we'll see. All right. Over here, we've got, oh wow, it's making some different options here. So we have our, I think this is PEO instead of PEI, but the main thing here is that it's got the, interesting pattern on it. So what I wanted to do, we could just print on this, I suppose, just some random shape just to see how it's going to work. This is PETG that's in here. Oh, you can't see it, but it's a blue PETG. Just a old sample roll. We could, why don't we try that? Just try printing on here. Let's see, this printer, I need to load up Cura. Cura's loading. We'll just try to print some kind of flat sheet. To basically all we're interested in is how well does this transfer. Now I do know that this printer doesn't like printing too close to the bed, so that might be an issue, because it does need to squish down into the bed pretty well. I've got it set to where this one does not squish too much, so we can adjust that a little bit, hopefully. I don't want it scraping into the surface though. That's not what we want. Might as well come back over here while it's loading Cura. So you can kind of see some of the things Some of they all look very similar except for this one. I don't know what's going on with this one. This is the 3-axis milling, and it just hasn't done much at all. It's done 7 iterations and basically nothing. These are starting to get different looking. This is the which one is this? Casting. So I don't know why it's keeping this little piece right here. That's doing nothing at all, but it's keeping it for some reason. You can almost start to see, you know, an I-beam, curved I-beam shape in there, which would be the strongest way to do that. You can kind of start to see a flange, and a web. I don't know why it's kept that part though. I assume it will get rid of that. Don't particularly like the way that these intersect with each other. That kind of looks dumb. But I told it to preserve all of this, so it's not going to get rid of any of that, and it doesn't think it needs any material out there. So it doesn't care about aesthetics other than it has a symmetry plane, so it has that. Other than that, it doesn't care. Let's see if Cura is opened yet. All right, here we are. I have not changed the nozzle, still 0.4 millimeter. Let's print first, and then we'll change the nozzle to the point. I think I was going to put a 0.8 in there. Let's just put a cube, and let's resize it though. Let's make it bigger, but way flatter. Because we don't, why is it doing, I don't understand how it's scaling there. Two millimeters thick, that's fine. All right, we don't need a lot of thickness to it. We just want to see how the bottom's going to connect. Let's see. So 0.2 millimeter, we only need one wall. This doesn't need any. Walls are slower than infill, so let's only do one wall. We don't really care about the top. Let's just do 2 top layers. The bottom is what we're interested in on, can we get this pattern to transfer. So let's do 3 bottom layers. That should get a lot of stability, you know, squish all for the bottom. Infill, that doesn't matter for what we're doing. This is PETG though, so let's go, let's just change it over here to generic PETG. What are these flow rates? Let's keep those changes. Oh, no, let's discard those and go back. One wall, one top layer. Oh no, let's do 2 top layers. One top layer is really kind of hard to do, although it doesn't matter. Let's do 3 bottom, infill 20, yes. Build plate, I don't know a good printing temperature for this. PETG does normally print with a hotter build plate. Actually, I normally print it with like 80, but we'll try 70. Print speed, that's a little slow, but it'll be okay. Fan speed, PETG is one of those materials where it can do any of fan off, on, but it's greatly affected by the fan condition, the layer cooling fan. So off, it prints really strong parts, like they're really well fused together, but they might be kind of lumpy and, you know, unattractive. All the way on 100%, the parts will come out looking really nice, but they won't have good interlayer adhesion, and they'll come apart pretty easy. So I usually do 50%. Actually, I usually do off for the first layer, which I think is what's probably built into here. Let's see. The initial fan speed, let's turn that one on and see. Yeah, so the initial fan speed for the first layer is usually off for anything I print, and that's what they've got here. We don't need support. We'll do our skirt just to kind of get the nozzle height right, and slice. Let's see how long this is going to take. 38 minutes, because we've got several layers that we probably don't need. We have 10 layers. Let's make it smaller. Let's make it smaller so that we can actually get it done in class time. So let's make it just an inch, and let's keep everything else the same. 9 minutes. All right. maybe that's enough surface area to tell us if it's going to work or not. We'll save that. I don't even know what it's called. Oh, well, we're about to call it, let's call it PEO test. Pretty sure this material for this bed is PEO. Okay, we can close that. Oh, you know what? Hold on. Let's go back over there. I gotta set up the Raspberry Pi to connect to something. It is connecting. All right, so now I've got that. Remember, this printer runs Clipper, so we do have to interface with the Clipper interface here. So let's G-code files. Let's upload our PEO test. I put it on the desktop. There it is. And let us print that. And it'll start heating the bed, heating the extruder, all that kind of rigmarole. Let's check out our SolidWorks. Not SolidWorks, Fusion. So we've got 3 that have converged. So converged means that it's satisfied with the solution and it didn't have some weird can't solve it at all. And then it still hadn't done much with, I think this was which one was this? 3-axis milling. Just hadn't done much. Not much is going on with the 3-axis milling. You know, done a little, it's done 14 iterations and not really come up with much. These are not as interested. It recommends this one. This one is sort of interesting. We're not getting all the little tendril stuff, right? We got like 2 little legs here, and then it left a web between this curved I-beam-ish shape. But that's kind of how this works. So from here, we can we can look at our different. I don't know if it's a transparent view. I don't know if that would, if there were internal geometries. Stress view, none. There's like no stress on it. Which one is this? Oh, this is just the unrestricted. Hey, if you can do anything, here's a shape you can make. This one did come out different from the others. It did use aluminum though. Design preview. That's the one that we were looking at before. Kind of like it gives the material finish on there. We don't need to see any of those, but if we were concerned that something had gone awry, nope, it's actually avoiding all of the obstacle. And it is preserving what we told it to preserve. We could compare it to some of the other preferred solutions, give it tags, and you can start to create geometry. So we could design from this outcome, or we could create a mesh like a STL file. Why don't we? Well, let's finish this. What is this? Oh, this goes back to the job status. Here's, I guess, the printed one. Yeah, this is the additive one. It actually added, that's weird. It actually added some material up here on the preserved region. I'm not sure why it felt like it needed to do that. Because there's not hardly any connection point between here and here. It's not like that's doing anything. So for some reason it thought it needed to add some material there. Let's look at the stress. Again, none, essentially. So if I were using this one, I would just chop those off because there's no reason to use those. Again, with our little 3-pound load, it's not really coming up with super interesting shapes for the stand, but there's what it came up with. Same thing, we could export either direction here. Maybe we want to go in and chop these little edges off because I don't think we need those at all. And then the last one, I think this one, this is the casting one. So It'd be a 2-part mold to cast that. That was not particularly interesting. This one's the most interesting, and I'm pretty sure we could go in and punch holes all in this web and make it a little more interesting, and maybe flare these out a little bit so they're not just kind of stuck on the base. Do something with the base to make it something other than flat. Let's see if we can get a mesh out of here. Printer hadn't started printing yet. It's still, well, it's got the bed up to heat, but it's going for the extruder. So we do need to go over to that pretty soon and monitor that first bit of printing. This is, okay. Alright, whatever. Still working on it. Let's go back over here. So what I'm thinking I'm going to need to do once it starts printing, 240 is a little bit hot for PETG, this PETG anyway. So I'm probably going to drop this down some once it actually gets up to 240. That's one downside to the way the G code is written here, is that it's going to wait until it gets to 240. There are G code commands to start, heating and then carry on, but you run the risk of it not actually getting all the way up to the temperature you want before it goes and starts trying to print. So, it's almost there. So I'm going to drop this probably down to 225 once it starts. All right. Now, I'm going to watch over here. Got some stringy. It's doing probing the bed and that kind of thing. Once it starts printing the skirt, I'm going to go back to here, and I've got a Z offset set of buttons where I can, while it's printing, raise or lower the nozzle. Well, it's really thinking I'm raising or lowering the bed, but this one, the bed doesn't move up and down. So I can raise or lower the nozzle to get it tuned in. Or I could go over here and change the knobs if there's like one corner that's different from the others. I think the last time I used this, it was pretty flat as far as all the corners being level, but I may need to bump the nozzle up or down uniformly across the whole plate. Now that I told it to cool down to 225, it's waiting and cooling down. That's why it stopped. Alright, we're at 240. Why did it go back up to 240? I don't know what it's doing. It must have sent another G-code command to get to 240, even though I told it to go to 225. So I don't know what it's trying to do. Now, oh, no. So what it's doing is, in the G-code, in the slicer, I guess, either one, the slicer or the hard firmware for the printer, it wants the bed at 50, which is actually a little cold for PETG. My small prints keep getting knocked off the build plate. I've set the... So for small prints to try and stay on the bed, either a brim or what I usually do is, I don't like the brim. The brim is good, but it attaches to the part and it's hard to remove on small, tiny little things. So I usually print small things on a raft. To try and keep them from detaching from the bed. It's basically like support for the whole part. The other thing the raft does is, if there are little tiny gaps or high spots or low spots in your bed, printing a raft on top of those levels all that out, and then you print on top of the raft, which should be perfectly level with your machine. It takes longer, it's more material. It takes an extra 10 minutes or so to print, so it has some downsides. Now that I'm seeing this, I do remember that this was a problem. I think in the printer file itself, it is set to go down to 50 degrees on the bed, and so it's having to cool down. Oh, on the preloaded temperature, you may have to make your own temperature tower then, because it doesn't have a raft, or you can't add a raft to a just G code, as far as I know. I guess you could, like you could cut and paste, but that'd be hard to do. It'd actually not be as simple as cutting and pasting. So you might have to go in and create your own temperature tower if you wanted to print with a raft. But a raft, I mean, the temperature tower is not this kind of small part I'm thinking of. I'm thinking of small parts like tiny little individual pieces, but that has a big enough base that you shouldn't need a raft for it. This thing, I see what's going on my printer over here. It has, in the machine code, if we can look at that for a second. So, in Clipper, you've got your firmware, your Marlin, all that kind of stuff. You go in and edit stuff, and then you reflash the firmware. Well, Clipper has a configuration file that takes care of a lot of that sort of thing. And in here, yep, right there, I have hard-coded in temperatures to go ahead and just have it set for, but this is PLA, and it's trying to use these temperatures. So the slicer told it to go to PETG temperatures 240 and 70, and then it read this start G code that's built into the printer's configuration file, and it's telling it to do these temperatures. So what we need is, I need to get these back to reasonable temperatures, because 205 is a bit cold for PETG. It is extruding, but it's not sticking to anything. So let's drop the it's heating up, and it's trying to heat the bed too, but we may have to change that because I don't know, we'll drop it down another 0.5 millimeters. So it is sticking down, and it is starting to get it's at a good printing temperature for the filament. The bed's kind of cold. There's our little square. It's not close enough to the bed. I'm dropping it down on off the screen. I'm lowering the nozzle. It's hard to see under there what's happening, but it was too high. I need to, let me go ahead and, while I'm thinking about it, change these temperature. I wonder if I should just leave these off. Maybe I should comment these out, so that we'll use the settings from the slicer. Yeah, it's kind of working. I might let it finish. Or I might just let it do this layer and then start the job over with the better settings. Maybe I'll let it do 2 layers instead of doing the whole part. I kind of feel like it's going to pull it off of the bed though. Also, this bed is not as sticky as PEI is, so you do have to have your settings pretty right in order for this to work. Yeah, see how messy it is? Yeah, it pulled loose. All right. So let's see if we got. All right, so this at least we'll reprint, but this at least does show you the pattern. I don't know if you can see it very well on the camera or not, but you can definitely tell it's shiny. And in person, now I think I could still get some more squish out of the bed. I lowered it down 0.2 millimeters total. But you can even get the little diffraction pattern on there. I just don't know how well you can see it on the camera or not. Maybe if I turn this light on. Maybe. Oh, yeah, there you can see it. You can see it. And it even gets some of the, like, the multicolor, not nearly as much as on here. Now, maybe if I used a black filament, it would show up better. But you can even get some of the diffraction or refraction that causes the color change. Let's reprint it with the other settings and see if that looks any better. I had to re-upload the. Oh, that's the other thing. So that I changed those configuration settings in that printer configuration file over here, and that was it. Like, I just re-uploaded that, so there's none of the recompile it, flash the firmware, and there's none of that kind of process that you have to do with the Marlin-based printers. That's one of the main reasons I like Clipper. Not the main reason, but it's a big part of the reason I like Clipper, is because I'm normally working on some kind of printer like this that's kind of all over the place, and if you're needing to edit it all the time, or try some different thing, it's super easy to change what would be the firmware, except it's just a configuration file. Let's go find our files. All right, let's see. I'm thinking about using PETG. Are there neat mods? Oh, no. So PETG is totally fine to print on an open air bed slinger, non-all metal hot end printer. It's all fine. The only thing with PETG is it's going to print hotter. So I've got it set at 225, but it might go up to 240 or so on some cases, which that, if the PETG you get has to print 240 or higher, then 240 is probably okay, but it will, that's the breaking point or the breakdown point of the Teflon tube inside your printer, particularly on an Ender 3 Pro. If you've changed out the hot end to an all metal one, not a problem, but the ones where the Teflon tube goes down to the nozzle, that 240 is kind of the limit. So, but most PETG you can print below that and it's fine. You do have to not modify, but you have to make sure that the fan, the layer cooling fan, this one, the one on the side over here, is 50% or so. Otherwise, you'll get different results. Turn it all the way on and you'll get nice parts that come apart. Turn it all the way off, you'll get very good layer adhesion, but it will kind of be lumpy. And then the bed is usually pretty hot. So I've got it set at 70. Some people print at 80 or more for the bed on PETG. But no, as far as just, there's none of that you have to change anything. No mods you have to make. It can print in the air. You don't have to enclose it or anything. It's just hotter bed. It's going to print hotter. And I think if I'm thinking right, the smooth PEI and smooth glass are not good for PETG. I think it'll stick too well to the smooth surfaces. Now this one, it's not. This was smooth, but it's not going to stick to it too bad. The textured surfaces, so the glass with the dots on it, or the textured PEI sheets, those are fine. But if you're doing like smooth glass or the smooth PEI, you might want to put something down like either tape or glue stick. Where are we at here? Oh, it's heating up the nozzle. So I don't think we're going to have time for our nozzle change. We've done that before, Maybe we'll do that very first thing on Friday. Let's check in on Fusion. Oh, it did. So it did complete this one, the 3-axis one. It looks like it just gave up. Oh, yeah, it says encountered a problem, failed to complete that one. So it just didn't do that. Printer did something and then it stopped. So I'm not sure. Error. M40. Oh, shoot. Okay. So it's under my picture over here. But in this console, can I move the console? No. It's giving me error on M140S. That's related to what I just changed. So, right here, where's the, it should, yeah, right there. So M140S is setting the bed temp, but I just, the variable named bed temp, I just commented out. So for now, just to make it work, let's do it this way. Well, let's make that 240 because that's what the slicer says. So now it'll try again. I need to go change that start code to what it needs to do is grab the bed temperature from the G-code slicer file and put it in, but I had hard coded it in. So it's got to heat up the bed to 70. On those G-code files for the bed and nozzle, there's one, I think it is the 140 maybe, M140. One of them sets the set point and lets the G-code carry on, and the other one sets the set point and waits for it to reach the set point temperature. So I think it's 104. Oh man. Let's see if we can find it. Here it is right here. So 140. Oh, so that's 190. This is weird because oh, okay, it's just giving me both of them. 190 is related to it. 140 sets the target temperature, but it continues without waiting, so it continues reading the G code. If you use 190, then it will set it to some number, 70 degrees, and wait for it to get up there to 70 degrees before it goes on. Then you have the same things for the hot end, except they're different numbers. It's I don't remember, 104 and 109 maybe for the, I don't remember what the temperature nozzle temperatures are, but they're similar. All right, so we've reached there. Shouldn't take very long to heat up the nozzle. Since I reset the firmware, or well, the configuration, it lost my Z offset. I did have to change that to -0.2 in order for it to look like it was going to print well. But we'll see what's happening here in a second. And maybe we'll get a better camera. I wonder if you can see this better on the other camera. Let's see. On this camera. I don't know. No, because this one's not going to autofocus, so it's not going to. Yeah, I don't. You can kind of see it. All right. Let's see what we're going to do this time. I'm ready with my Z offset button. On this Z offset, there is also a similar command in plain Marlin that you can use on your screen here. If you have it enabled and you're printing, it's doing something, you can double click this knob and it will go to a tuning menu, and there's an option called baby stepping. And baby stepping is the same thing. You turn the knob and it will drop the nozzle down or raise it up, whichever way you're going. And it does the same thing. Let's see. That's not. Let's go down. One thing with the baby stepping and the Z offset, it occurs on the next line of G code. So it has to finish one line of G code, whatever, go from here to here or whatever it's doing, and then it will do the baby stepping. So if you click a bunch of times and nothing's happening, it's because it's still working on one line of G code. This is looking much better. So now we're printing at 240 and the bed is at 70. Like I said, the bed could probably be hotter for PETG. 70 is probably kind of the minimum that you would want to do for PETG. But this is looking like it's much more likely to succeed than what we'd had that first time. There is still one line that's kind of out of line. I'm not sure what happened to that line. It's not lined up with the others. Not this one, but one in the back. I don't know if you can. Yeah, this one right here is. That one is. I'm not too worried about. That was part of the skirt where it didn't stick down. I don't know how close I can get in there. Oh, I can't. It won't. Oh, it's kind of lumpy looking in that picture. So that, and I can see it in person. So that lumpiness that you can see, what that is I am over extruding or my nozzle is too close to the bed. Now I'm not particularly worried about it because I'm more interested in getting a good squish on the bottom side, and that lumpiness is going to get covered up. But if you see that kind of lumpiness in the first layer, you're putting too much filament out for the amount of space you have to put filament in. Sometimes it'll show up as like waves in your first layer. All that means is in that area, either your nozzle is too close to the bed or you're putting too much filament out. So I'm doing both. I've got the nozzle really close to the bed and I'm over extruding a little bit because I want that first layer to really squish in and imprint this pattern onto the bottom of it. So if you're worried about that, those are the things to change back. Usually it's just raise the nozzle up. In this case, I'm intentionally doing it so that I can get the good imprint, because this surface texture needs to actually be embedded in that bottom surface. So that's why I wanted a good squish. Oh, hello, DaVinci 10. Let's see, so how long do we have left on this thing? Technically, we've probably got what we needed, but it's going relatively quickly. I'll let it do this first layer, and then we'll speed it up. So over here, again in Clipper, you've got a speed factor, and you can just multiply it by whatever thing. Over here, if you're not using Clipper, you're using Marlin. Well, we're way zoomed in on your control panel. On the printer itself, you can click that button and there is a tuning menu. If you click it once, it brings up a tuning menu. Click it twice if you have it enabled, and it will bring up you to baby stepping, which is the Z offset. But click it once and there's tuning menus for, you can tune the flow rate on the fly, you can tune the speed on the fly. I think you can tune the fans on the fly if you want to, but you could just increase the speed if you wanted to, if you thought it was all going well. Now I think it's going well. Let's 200%. So you heard the change in pitch. For one thing, it's on the second or third layer now. I'm not sure which layer. It's on the third layer, and the first layer of all prints, unless you've changed it, they are going to print at half speed of whatever you set, just to try and get that first layer stuck down. So it would have changed sped up anyway, but I went in right over here and changed the speed factor. Same thing as if you went in over here, click this and change the speed also. I just want to get it done. I'm not particularly worried about the part. I just want to see the bottom of it. So these little layers don't matter too much. Sometimes if you print too fast, well, there's a lot of things that can happen, but one thing you might have to do is raise your printing temperature, because it has to push out more material, which means it's got to melt it faster. And so if you do increase your printing temperature, however you do it, you probably need to print at a little bit higher nozzle temperature. In this case, I was already printing at what is, I think, a little bit high for PETG anyway, so I didn't raise it. But now we're 82% done. It's really messy too, but again, I'm not worried about that. I just want to see the bottom layer. And I think when we sliced this, we only did maybe 1 or 2 top layers. I think I did 2. So they're not going to look great. But they'll be okay. Oh, we went 1 minute over. But I want to see what it is, and then we'll shut down the stream. So if this comes out interesting, maybe I think I have some black filament. It doesn't have to be PETG either to make this pattern work. Any of the filaments will work. Maybe some of the matte ones may not work too well. I don't know. But let's see. PETG is what I had loaded in the machine. It's there. Now again, can you see it on the camera? I don't know. So the shiny is because this is a relatively shiny surface. You could get that effect with just a piece of glass or whatever. But there, you can kind of see the, you can see the pattern and the different colors in there. So that can be pretty useful if you, and there's all sorts of patterns. Even this sheet, the other side of it is a different pattern, so stars. But there's some that look like carbon fiber. There's different chopped fiber look. Or forged carbon fiber look. So there's different ones, and they all will give you some different patterns on the whatever you print on the bottom side. So you have to orient your part so that maybe it's a control panel or whatever, the part that you're actually going to see ends up facing the bed, and then it'll put that pattern onto your surface. Kind of like the textured PEI, except these add a little bit more interest. I'm noticing that I still didn't get a lot of squish in there. You can still see some layer lines in the very center. I don't know, it's hard to get it to show up on the camera. But you can kind of tell that the layer in the middle, or the layer line, or not the layer lines, but the bottom layer lines, I guess, in the middle didn't quite squish together, but kind of neat. It does have the issue of this material doesn't hold the same as glass or PEI, so you do have to get your settings right for whatever material you're using so that it actually sticks down pretty well, because it is harder to adhere to this, and you don't want to put any, like if you put tape on it, obviously you're not going to get the pattern. If you put glue stick on it, you're not going to get the pattern. So you can't put any kind of adhesive on there of any sort, or you lose the idea of the whole pattern to begin with. So you have to print straight onto the surface, which can be a little bit challenging, but we at least got that to print. All right, we'll come back Friday, and we'll do the nozzle change to the 0.8 millimeter and see what we can do with that. And we'll probably do some other stuff. We still need to do a couple of things with our plane. Oh, yeah, this. I did get in the heat transfer stuff. So I have one for laser and inkjet, and one that's just inkjet. I will print some patterns on these and see if we can get those patterns to imprint on, or transfer to, not imprint, but transfer to the printed plastic. So basically we'll print our pictures on here, put this on the bed, print on top of it and see if we can get the transfer to happen that way. We'll see what happens. Should be able to try that at least on Friday. All right, I will see y'all on Friday, and think we're good for this